All right, today we're going to finish up section 2.3, which is other set operations. And you're telling me we were right here. Yes. Does that look right? Wonderful. All right, so we're using Venn diagrams to talk about how to shade these types of sets in. I know that I talked in the video you watched about the fact that you actually have to go through the steps that I'm telling you in order to verify that the work you're doing actually gets you where you need to go. I mean, like, that's part of the process. It's like if you were working with a child and they're doing like addition of like 3-digit number plus a 3-digit number, and all of a sudden just magically out of nowhere they come up with the answer and you're like, something sounds a little off about that. Where'd your calculator go, right? Like, they weren't supposed to be using one, of course. Okay, so we're working with this in a way that we actually have to show certain pieces of work to make it make sense. And since we're working with a diagram with 3 letters, A, B, and C, we need a diagram that has 3 overlapping circles. And there's really nothing special about the order of the circles, except to say that if we put them all in the same circle, you're far less likely to the grader counting you wrong because they'll know that it matches whatever they've seen before. So it just makes it easier for us all if we have them in the same way. I didn't mean for that to be a U. That's a C. There's my U. Perfect. Okay, and as well, there's nothing special about putting numbers in. I choose to put numbers in. Some books will put letters in these places as a placeholder. But because my sets themselves have letters, I kind of like using something different. So numbers work best, I think, for me. So here's 1, 2, 3 across sort of the middle, or at the top. And then across the middle, I have my 4, 5, 6. 7 is in the bottom circle, C with an 8 on the outside. Okay, so as we're looking at the statement that we're trying to shade in the portion of the diagram for, just like with algebra, we want to start with what's on the inside first. So what's on the inside here is A and B complement. So the first thing I'm going to do is I'm going to write down what numbers are inside circle A and what numbers are inside the portion of the diagram that relates to B complement. So circle A first. What numbers are inside circle A? 1, 2, 4, and 5. Now, B complement is the outside of circle B. So what numbers are outside of circle B? 1, 4, 7, and 8. And then we consider what symbol is being used to compare these two sets. What does this symbol mean? It means and. Intersection, overlap. What do they have in common? So looking at these lists of numbers, 1, 2, 4, 5, 1, 4, 7, 8, what do they have in common? 1 and 4. So what we have found out by doing this portion of this, oops, hang on, let me try that again. The stylus is not cooperating this year with me. Is that A intersect B complement, hang on, there we go, is 1 and 4. That's what we've just found out. So that's everything inside of the parentheses is now complete, and we move outside the parentheses. So on the outside of the parentheses, we have one more set mentioned, the set C complement. So before we go trying to join it with anything, we need to list what it is. So we've got circle C, and complement means everything outside of circle C. So what numbers are in the regions outside of circle C? 1, 2, 3, and 8. And then again, we look back at the symbol that joins the part that's in parentheses, A intersect B complement, and C complement. And we have another intersection symbol. But we wouldn't have to, right? It could be a union symbol. It doesn't have to be the same. It just happens to be this time. So intersect again means what do they have in common? And that would be what number here?
1.
It's the number 1. So what we've just found out is that A intersect B complement, intersect C complement is actually just the number 1. So this is all the work that verifies my solution. My solution is that I'm supposed to shade that portion on my diagram. that's the solution. That's the answer. If you only give me that shaded and peak region and you don't show me any work, we got issues. But likewise, if you do all the work and fail to shade in the pink region, you haven't quite finished the problem. Okay? All right, so the numbers that we've used up to this point have simply been placeholders. They're sort of labeling a space, right? Like the number 5 doesn't have anything to do with the value 5. It's just a placeholder. The next problem actually changes that situation. So in this problem, they're actually telling you that the cardinality, the number of items in set A, is 24. That the cardinality, or the number of items in set B, is 24, and so forth down the line. So we're going to start the problem much like we did before, but we're not going to put the 1, 2, 3 to 8 in there. That's not going to happen. We're just going to put our circles inside of our rectangle. Okay?
Do we still put A, B, C, and U?
Yes, you will. You'll still put A, B, C, and U. So here's A, B, and C inside of our universal set U. Okay, so far so good? All right. Now here's the deal. I want you to take a look at the set A. Now when we did the problem over here, we had the numbers 1, 2, 4, and 5 inside of circle A, right? Because there's 4 specifically different areas or regions inside of circle A. Some of them overlap with A and B, or with B, some of it overlaps with C, some of it overlaps with nothing, right? I mean, there's 4 different areas that are inside of circle A. What this is telling you then, the very first piece on here, is that all 4 of those areas inside of circle A have to combine in total to represent 24 elements. So some of those elements are in part of the A that's not overlapping everything. Some of those elements may be in the part of the A that overlaps B and C, right? So if I want to take 24, I don't really want to start there because I don't want to have to figure out how to break the number 24 apart into 4 separate numbers, all adding to 24 that continues to make everything else work. This starts to feel like a Sudoku puzzle, right? Like there's so many things that I could put here, and if that's the case, that's probably not where I should start. I have so many different options if I start here at the beginning. Now the same is true for the second statement about circle B and the third statement about circle C. None of those 3 are a good place to start. Now if you look at the second line of text, it says the number of items in A intersect B is 10. Now A intersect B is this portion right here that kind of looks like a football, right? There aren't 4 pieces within that, but there's still 2. So I can use 0 and 10, 9 and 1, 1 and 9, 8 and 2, 2 and 8. There's still a lot of possibilities, right? And the same is true for the B overlapping C and the A overlapping C. So that middle line, probably not our favorite place to start either. The last line, however, says this is the number of items in A intersecting with B intersecting with C. Where is that?
In the very middle.
Yeah, it's this piece right here. It's like a goblet or something, right?
Yeah.
Just the top of a goblet. All right, that piece right there has 1 region in it. So there's no guessing. I don't have to try to divvy up a number into 2 different places or 4 different places to make it work. It's very specific. This piece right here gives me 6, and a 6 is going to go right there, and I'm done with that piece of information. The last piece of information is the least helpful of the whole thing. I mean, you need it later, but it's super not helpful at the beginning of the problem because it's telling you that everything in all the 8 regions total adds up to 50. So that's not helpful information right now at all. I have lots going on in this puzzle, if you will. I don't need it to all add up to 50 right now. Not useful. But the cool thing is that if I move up a line into this line now, it's all very useful. So this first piece right here that says A intersect B, that was the first football I drew down here, right? Originally, I said there's 2 regions, and there's still 2 regions. I just know what one of them is already. It's 6.
So you go to 4.
So the other piece of it must be 4, or they wouldn't add up to 10. Okay, so now I've taken care of both of those pieces of information, and they're done. So now I can go over here to B intersect C. So B intersect C is over here. Again, there's a 6 already in there with 1 region left. How much will go in the outer region of that circle, or that overlap? 2, because they're supposed to add up to 8. And then the last piece through the middle is A intersect C. So that's over here. All supposed to add up to 15. So how many am I missing? 9. And that piece is finished. That's 4 of my 8 region pieces that are filled in with their actual cardinality now. And again, 4, 9, 6, 8, 2, all the numbers that are there, not an 8, sorry, 4, 9, 6, and 2 are all representing how many elements are actually in that category. And we're going to create some, we're going to have context so you can see how this plays out in a minute. But these are actually like numbers of people or whatever, responses within a category, okay? They're not just space holders. If I go back to my top line, however, now, like the number of items in set A, all of this is set A. There are 4 regions, but I know what's in 3 of them. So how much do I already have represented inside of circle A? 19. How much is it supposed to be? 24. So how many are missing? 5. It's 5, yeah. It's 5. All right. Circle B is also supposed to be 24. How many are currently in circle B? 12. So how many are missing? 12. Now that circle all adds up to 24. And we're done with that piece. Now we have circle C. It adds up to 26. How much do I currently have represented in this circle? 17. So how many am I missing? 9. Almost everything's filled in. What's missing?
50.
Yeah, the information that 50 will allow me to find, but what's missing in the picture? The part that's on the outside of you, right?
Yeah.
That's in the outer region, outside of all my circles, that part's missing. It's not 50 though. So how am I going to use that 50?
Subtract it from all of this other stuff.
Yeah, I need to add up everything that's inside my circles and take that sum away from 50. So what do you get if you add up everything that's inside of your circles? It is 47. So how many are left? 3. There's a 3 out here. Okay, so this problem, every time I do it, I feel like I'm doing a Sudoku puzzle. It's just like process of elimination, figuring out all the pieces, and so forth. But there's a reason why we're doing it beyond just the fact that it's a puzzle and puzzles are fun. There's actually a purpose, and it actually shows up in the next problem. So Venn diagrams allow us to make decisions about overlapping pieces of information. So this is a relatively straightforward one. The next one's a little bit harder. Joe Long works on albums for musicians. Last year he worked on a total of 12 projects. He wrote and produced 2. He wrote a total of 5, and he produced a total of 7. Okay? And then there are some questions that follow, and they are not where we need to start. We need to start by creating a Venn diagram to represent the situation. Once we've done that, the questions become very easy. So let's take a look at Joe. Joe's, world, in the sense of this problem anyways, this rectangle, it's the universal set. And how many different circles am I going to need to represent this situation?
3.
It's 2. Why is it 2?
Oh, because you combined the middle.
They'll overlap, yeah. So there's only 2 different things that are going on in this problem. What is Joe doing for this musicians? Writing, producing. At least those are the only 2 things mentioned, right? Writing and producing. So even when I draw my circles, it might even be helpful, instead of labeling them as A and B, to label them as to what they represent. These are the ones he writes, and these are the ones he produces. Does that make sense? Okay, so you got to have the structure in order to be able to work within the rest of the problem. So we have 3 pieces of information. I've actually already underlined them. One that says he worked on 4 pieces of information. One that says he wrote and produced 2. One that he says he wrote 5, and the other one that says he produced 7. What is the most narrow piece of information? The wrote and produced. Where is that on my diagram? In the middle. It's the overlap. So he wrote and produced 2. So over here, that piece of information is now complete. I'm done with that. What piece might you want to start with or go with next? Wrote 12 is going to be our last piece of information because, I'm sorry, not wrote. Worked on 12 is our last piece of information because that has to represent everything going on, and that's still a lot of regions. Do you want to do 5? Okay. Danielle says we're going to do 5. So it says he wrote a total of 5. So the 5 has to be everything inside of the wrote circle or right circle, whatever you want to call it. I already have 2 in there, so how many more do I need? 3. And now everything inside that circle adds up to 5. And I'm done with that piece of information. So where would I go next? Produces 7. So here's my produces circle. I already have 2 in there. I just need 5 more. And then the only piece of information I haven't done is the worked on 12. That does not mean I put 12 on the outside, right?
Yeah.
It means that all 4 of these regions have to add up to 12. How many do I already have? 10, so I need 2 more. So these 2 on the outside, he did something else. He didn't write them, he didn't produce them. Maybe he sang, maybe he banged on a drum. I don't know. He did something different, right? So once we have all those pieces filled in, we can answer the question that's posed. Part A says, how many projects did he write but not produce? That's my 3. You got it. Do you see how easy it was to just look at my picture and answer it? Instead of just looking at all that information above to make that decision? The next one says, how many projects did he produce but not write?
5.
That's 5. And the last piece says, how many did he neither write nor produce? And that's the 2 that's on the outside. All right. So here's what we need to do. I have 3 minutes left, which is not enough time to finish my last example of Venn diagrams. Let me skip to the last example in total, which is right here, the Cartesian product. So we'll do example 6. Next time we'll come back and we'll pick up example 5. However, I would like for you to start working and get as far as you can on the homework, because next time is our review session for our test on Friday, and you won't have another opportunity in class to ask me questions. So if you encounter questions on the homework, I'd like to be able to answer those in class on Wednesday. But you don't need to do the group work. You can do the group work in class on Wednesday as well. Okay, so just push pause on the group work, do the homework first, but recognize you're not turning it in on Wednesday. But I really would like for you to look at it so that you can ask questions if you have them before you are done with me until the test, okay? So let's do this question right here. It talks about Cartesian product, which we haven't talked about today, but you saw a video on it over the weekend. Is the Cartesian product commutative? Why or why not? So the Cartesian product, if you'll remember, had to do with taking elements in one set and elements of another set and pairing them up, right? Taking pairs together. We talked about one of the examples of that is our ordered pairs for our like XY plane, right? The numbers on our XY plane. So the Cartesian product is the idea of asking the question whether if you pair the numbers up like this, is it necessarily the same thing as pairing the numbers up in the opposite order? And in general, they're not equal. And the easiest way to think about it is in terms of our Cartesian coordinate plane, right? If you had the ordered pair 1, 3, that's here, and you have the ordered pair 3, 1, that's here, and those are not the same location in space. So does that mean that it could never be equal? Well, no, it could be the same, Especially if the numbers do happen to be the same for this particular example, even it would work, right? What if they were both 2s? 2, 2, 2, 2. It's all the same. It's good. No problem. Order doesn't matter. So the reality is that in general, the operation is not commutative. And our example showing a place where it doesn't work is that 3, 1 does not equal 1, 3. Right? As a Cartesian ordered pair, that doesn't work. You could use lots of other examples as well. That doesn't mean that you can't use examples that would work, right? We can do that.
0, 0.
Yeah, but we need to make it work for all examples, and it doesn't work for all examples. So in general, it isn't true. All right, so we'll pick back up next time. We'll go back and get example 5 first. We will do homework questions second, and then we'll do group work and talk about the test third, because we haven't had a test in this class especially yet.